Okay, first hour, this is for you to help catch you back up here. So you are watching this video on Monday, and we're getting ready to do investigation 4.1 and 4.2, which is relating body measurements to negative correlation. So we're getting into what we call scatter plots and um, all that good stuff. Let me shrink that. Um, so it says here our focus is if you have data relating two variables, how can you check to see whether a linear model is a good fit? How do you know if the relationship between two variables is positive or negative? So if you take a look at our first table, we're dealing with arm height, how tall you are, to arm span. So basically when you widen your arms out, fingertip to fingertip. So that's what we're comparing. They got these random heights in inches. You can see anywhere from up to 68 as low as 56 and the arm spans to match. So what your first task is you're going to do is you're going to analyze this data, all right? Um, you're going to take this, you're going to make a graph, you're going to plot your points. So when you make your graph, let's get you some space here, okay? I'd recommend making a big old graph and making some space. And we're just going to start, instead of starting at 0, we're going to start at 50. And we're going to continue to go up by 2s until we hit 70. So you should be following along doing this with me right now. We get all our points in on both axes up to 70. Okay. So what I want you to do right now is I'm going to bring my recorder back up here. What I want you to do right now is pause this video in just a second here. And I want you to go ahead and plot your points and see what you think. And then ask yourselves this question once you have it plotted. Do you think the scatter plot supports the claim that arm span and height are about equal for most people? So it'll take about 5 minutes. I want you to pause this video and we'll hit play in about 5 minutes. All right, we're back, and as you see, these points magically appeared. So your graph should look something like this. And what we see here, this is called a scatter plot. These are not linear lines, but you can kind of see they kind of have a positive slope. You can kind of see how the points, for the most part, as your height, which is down here, by the way. I'm going to label this graph. This is your height, and this is your arm span. So you can see as height increases, arm span is kind of trending upwards. So in terms of if you thought it supports it, you know, you could really argue both arguments. You could say that yeah, the points tend to be going up in a positive trend. So you could say it supports it, although it's not, you know, super accurate. It still supports it. Or you could say that, you know, since the points aren't linear, you know, it doesn't really support it. But you know, for the most part, the data you see here does move up in a positive trend. Again, it just doesn't. It's not entirely precise. All right. All right. So if you turn the page to page 2, this is where things will get a little. So it says if each student in the class had an arm span S equal to height. So for example, if their height was 3, their arm span would be 3 feet. Or if their height was 60 inches, their arm span is 60 inches. What equation would you relate the two variables? Okay. Well, what's the equation going to be? If it's equal to each other, it's just going to be S is going to equal H. Arm span is going to equal the height. So they want to take that equation and graph it on our graph. So let's go back, and you might need a ruler for this. Okay, I'm going to shrink this a little bit. I'm going to cheat and use my straight line tool since I don't have a ruler for the smartboard. So we're going to get our line here. I'm going to make it a different color. And I'm going to start right at 50, 50, and I'm going to try to go up. and a nice 1-to-1 as close as I can. All right, so there's my, so again, if I'm at 52 at the height, 52 should be my arm span. So again, you should see that roughly right about here where they meet, it's on the line. So I'm trying to make my lines very linear. Now I'm pretty close, so you can see 54. I'm a little under 54. I might have to bring my line up, but you get the idea, right? So there's our line. So it says here, which data points for part B, number 3, does your line pass through? We don't really pass through anything. We get pretty close about right to this one. Oop. We get pretty close to about this one right there, but that's about it. Um, so if any points that you made fall right on your line, what that means is that the model you made is that those points are pretty accurate in terms of for that height to the arm span. Obviously, the points if they don't fall on the line, obviously they mean a little bit different things. And again here, it says choose several points that are not on your line. Explain how the arm height is related in each. How do you describe the relationship shown in the graph? Well, again, if you see the points that are closer below the line, okay, um, basically tell you that arm span is less than the height. And if you see points above the line, that means arm span is greater than the height. So if we go to answer that question, okay, so if I want to do part C here off to the side, so if the points above the line show arm span is greater than the height. And if the points are below the line, it shows that the arm span is less than the height. Okay, so kind of like you see a visual there of greater than, less than. Okay. All right. So as we're going here, it says the tallest person in recorded history is Robert Pershing Wadlow. At age 22, he was 8 feet 11.1 inches tall. So that's 272 centimeters. His arm span was 9.575 inches. All right. Now, if you take a look at your graph that we had in the very first page, right, we're going by inches here, right? So, if he's 8 feet 11.1 inches tall, all right, 8 times 12 is 96 plus 11.1. All right, so height-wise for him in inches, he's 107.1 inches. All right, and his arm span, if it's 9.9 feet 5 3/4 inches, all right, his arm span is 113.75 inches. Because again, you take the feet, multiply it by 12, and then you can add the inches to it. That's how many total inches he is. All right, he's a pretty big dude. So where would that point be? And would that point be on the line of the graph that we drew in part 3? Well, if you go back to your graph, all right, let's get that number again. So he was 107.1 and 113.75. So that number, if you look at our graph, went the wrong way, sorry. All the way down here. Well, 107, I mean, you're talking I mean, we're at 70, we finish here, so we're talking way off to the right and then extremely vertical, all right? So that point is, I mean, we'd have to make a huge, huge, huge graph just to fit that point from where the majority of our data points are, don't we? So it's not even close. So if you kind of guesstimate where your line is going, more than likely, um, because his arm span was greater than his height, it would have to really fall above the line. Now, in terms of that point, it says, does the data for Robert Wadlow support the claim that arm span and height are roughly equal? It's hard to dispute that because it's not really on the line; it's above the line. But his dimensions are so much bigger than ours. If you look at the points in the actual data chart itself, I mean they're within a couple of each other. I think the greatest difference between height and arm span is 3 inches. Oh, there's one that's 4, but for the most part, you're dealing with 1 to 2 inches, and you have to, that's it's pretty close, 1 to 1. Where him, you're talking of a difference of over 6 inches, and that's not even close. All right, so we're gonna get ready to move on to part C here. All right, so we are moving on to the next page, which is kind of the combination of 4.1 and 4.2 combined. We just kind of finished the 4.1 part. So in 4.2, you see a chart up here, and we got race time and race age. And you're going to need your books for this part. So if you do take your book out for this chart, because the table is not in the book. So if you open your books to page 85 and 84, 85, 84 has the table, okay? And then obviously you have the chart right here on your graph. So they've drawn a line for you. All right, so this line drawn models the relationship between age and race time. So again, they're trying to make a linear model for like predicting purposes when you're dealing with a scatter plot, which is not precise. All right, so their first question asks you, what is the approximate slope of the line? So we're looking for a couple points that kind of hit the line pretty good here. And we got this point here. And if you look at your table for the student age, which is 8, it's the highest value. So that way there's an 816, an 817, and an 815. So this is 817. And this point, there's a couple points that really hit the line, but this point that I just drew here hits the line more than the other one. And that's off of 11. It's the highest value of 11, which is 1115. Because if you look at age, student age, you got two 11s. The race time is 13 and 15. All right, so we're going to use those 2 points. Well, remember how we found the slope of a line before? The slope of a line is y2 minus y1 over x2 minus x1. All right, so I'm just going to go 17 minus 15 and then 8 minus 11. So I did the 817 point first, so there's the y value of the first point, and the y value of the second point. So I get 2 over negative 3, which is negative 2/3. So roughly the slope of that line that we have there is negative 2/3. How does the slope help you understand the relationship between age and race time? Well, technically with that line, basically as your race time decreases, your actually let me go in right. So as your age increases, your race time decreases. So the thought is obviously as you get older and a little stronger, you get faster. Obviously once you hit there's a point once you hit 2 where that number goes back up eventually. Trust me. All right, number 3 says, do you think it makes sense to predict the race time for a 7-year-old using the line? If so, let's predict it. So if you go back up here, okay. Well, if I go here to 7, I'm going to just use my straight line tool. And I'm going to go straight up here. So I can see I kind of hit the line about right there. Now it's hard for me to accurately predict what that number is. So let's just say we're close to 20. I mean, I think that's a kind of a fair prediction, you could say, because it kind of hits the trend, especially if you look at your graph of a 7-year-old. It falls in between that. There's a 22, 23, 25 seconds, and an 8-year-old, there's an 18, 16, and a 17. 20 kind of falls in that data. I mean, I'd say that's a fair prediction. Um, and that if you were to predict that, I think they'd be pretty confident that you'd be fairly close there. All right, so but here's the one that kind of doesn't make sense. Do you think it makes sense to predict a race time for a 21-year-old using that line? Well, if you look, that race time hits just about 10 at a 16-year-old. 10 seconds is Olympic speed. So obviously that line is going to go down. That line continues to go down for a 21-year-old. You're basically thinking the fact that a 21-year-old could run a 5 or 6-second 100-meter dash. And that's almost impossible. Okay. So if I'm going back up to this graph here, at 16, a 21-year-old, their point's going to be somewhere out here. Okay. Well, the world record is in the 9s for that race. So if you're saying at 21 years old you can basically be faster than the fastest human being, I don't think that's correct. So I would definitely say that data is incorrect. That line, obviously, once you hit a certain age, and you can only get so fast, you're not going to get faster. And of course, once you even hit your 30s or so, you don't get faster. Trust me, you get slower. All right, so that was our 4.1 and 4.2 model. Let me show you your homework. I'll blow this back up here. And, oops, I did not get the slide. I apologize, first hour. So again, you should have some class time to work on this. It's page 96 and 97. That's problems 1 and 2. And then you got we're going to go backwards here to 71, and you're going to do problem number 9. So those are the 3 problems that you're going to work on. This is Monday. We're going to check this on Tuesday. So just make sure you have your work done, and hope you found this video helpful. And obviously, if you need it a little later too, you can watch this at home. So this will stay on our website. Thank you for watching, and I'll be back tomorrow.